Hello, hello. Bunch of you asked for uh walkthroughs, more video stuff, so I thought I would do that for you. Let me get this. All right. There we go. Alrighty. So pull up that. Okay. Uh so let's walk through. Let's see what we've got. And hopefully this will be helpful. So just going to go in order. Number one, a group of students played a game in which they earned points for answering questions correctly. The following dot plot shows the total number of points earned by each student. So here's our dot plot. Which of the following is the best description of the distribution of points earned? Okay, so looking at our answer choices, this is all about shape. So let's just process of elimination. Does this look approximately normal? No. By now, I don't think anyone picked that. Good for you. Definitely not normal. Next up, bimodal without a gap. Underline that, without a gap. Well, I can see where they're getting bimodal, right? There's two distinct peaks here. But this looks like a pretty good gap to me, right? There's a bunch of area without any data points and then a cluster of data points down here. So I would say the without part is what's wrong here. I'm going to cross that out. Bimodal with a gap. Yeah, that looks pretty good. It's got two distinct peaks, and then there's definitely this gap right over here. Just to be sure, I'm going to check skewed to the right without a gap. So again, if without a gap was what made B wrong, without a gap is what makes D wrong. It's also not skewed to the right, but we don't even have to think about that because there's definitely a gap. And then skewed to the right with a gap. So the gap part, yes, but it's not skewed to the right. Remember, skew is talking about where the tail is. So this would be what skewed to the right looks like, and then maybe a gap, a few data points to the right. So it's not skewed to the right. It's definitely bimodal. It's got two distinct peaks with a gap. Here's that gap. Good. Onward. 2. The table shows the responses from 103 people when asked if they support a proposal to expand the public library. One person from those who responded will be selected at random. Which of the following is closest to the probability that the person selected will be someone who responded no, given that the person selected is age 55 or older? Okay, so the reason I made such a big deal about given is given that the person selected is age 55 or older, we now know we are just interested in that, because this is everything about age 55 or older. So this is going to be my denominator. I'm going to go ahead and do that. And then will be someone who responded no. So here's yes, here's no. 36 responded no. So I'm going to get 36 over 44. That's definitely more than half. So just gut check, right? 36 over 44, a lot more than half. So A is out, B is out, and C is out, because none of those are more than half. This, is it more or less than half, is a really good way to just catch yourself from having brain farts. When I pop that in my calculator, I get 0.818. That's one of our answers. That's lovely. So again, given sets your denominator. And then someone who responded no, within that group is what sets your numerator. Okay, onward. 3. Data were collected on the fiber diameter and the fleece weight of wool taken from a sample of 20 sheep. The data are shown in the following graphs. Graph 1 is a scatter plot. So this is our scatter plot of fleece weight versus fiber diameter. So fiber diameter and fleece weight. Always check your headings with the respective least squares regression line shown. So here's our least squares regression line. From that data, here's the line that it would create. Graph 2 is the associated plot of the residuals versus the predicted values. Okay, so here's our predicted fleece weight and our residual fleece weight. It's really, really important that you understand and kind of clock the difference between a scatter plot and the residuals. Scatter plots should have a reasonable pattern, right? It looks line-ish. Residuals shouldn't look like anything. Residual plots. Okay, so 1 point is circled on graph 1. Here it is. 5 points labeled A, B, C, D, and E are identified on graph 2. Which point on graph 2 represents the residual for the circled point on graph 1? Okay, just a quick review. Residual is equal to the actual minus the predicted. So you could do this without calculating anything, but maybe it's just easier for your brain to wrap around numbers versus concepts. It's just a little more concrete. So let's look at this point. The actual is the actual fleece weight. So this is important. Fleece weight and predicted fleece weight. That is what is going to link these two things. So the actual fleece weight for this point is about 5. I'm not going to get too fussy with it. That dot is around 5. Minus the predicted, so I can just go as straight up as I can. That's where the predicted point is on our least squares regression line. The LSRL is our predicted values in a line. And it looks to be about 10, right? Our predicted is about 10, which means our residual is -5. Okay. Now, we can translate this information to this graph. So notice that the x-axis says predicted fleece weight. Our predicted fleece weight here was 10. So we want to find where the predicted fleece weight is about 10. So right away, we're down to C, D, and E. There's a lot of reasons why you might have thrown out E already, but these 3 have that predicted fleece weight around 10. So I'm going to cross out A and B. Okay. Now, the residual fleece weight, we got a negative residual. So E we can knock out because its residual is positive. The residual fleece weight is up here around +5. So E is out because it shouldn't be positive. Then we got a residual of about -5. So if we find on the residual fleece weight around where -5 would be, it's definitely closer to C than to D. D has a residual of about -3, but it's definitely more than that. So the only option here really is C. Cool. So when you have a scatter plot and a residual plot, you want to pay attention to what your axes are. So the predicted weight versus the fleece weight, or is it diameter and residual? So figure out what is linking one graph to the other. And sometimes x-axes become y-axes or vice versa. So be careful. All right. Numero 4. The distributions of 4 variables are shown in the following histograms. Which of the following shapes is not represented by one of the 4 distributions? Okay. So again, let's process of elimination this. Uniform. Be very careful. A lot of you are still occasionally mixing up uniform and unimodal. This, unimodal. Cool. This, unimodal. This, unimodal. We don't have a uniform distribution. That would look something, if here are axes, a uniform distribution would mean that each bucket or each bin is about the same height or is the same height. So really, really careful with uniform versus unimodal. All right, so it's not uniform. We don't, oh, well, which of the following shapes is not represented? It's probably this one. Let's just double check that the rest of them are there. And I'm seeing that this is a really tall question. Let me see if I can. It's easy to see. Okay, cool. So bimodal, this looks pretty bimodal. It's got two distinct peaks. Skewed to the left, we've got our tail area here in the left, so we have a representation of skewed to the left. Skewed to the right, it's not super skewed, but there is more of a tail on the right side, so that would be skewed to the right. And then last but not least, symmetric and unimodal. This is roughly symmetric and unimodal. It's definitely unimodal. It's roughly the same right and left. So it is represented. Now, our answer is uniform. I highly recommend you do what I did not, which is if you see the word not, circle it, underline it, because as you can see, it's so easy to forget it. Like it's there, obviously, but it is, for some reason, our brains just don't care. All right. Cool. Number 5. A random sample of 1,092 people were asked whether color was important or whether color was a consideration in buying a new car. They were also asked to identify one additional feature that was important. The responses are shown in the table. Okay, so we have a lot of info here. Which of the following is closest to the proportion of people who responded no to color consideration and who identified safety as the additional feature that was important? Okay, so no to color consideration and who identified safety as the additional feature that was important. Okay, so no to color consideration, that's here, and who identified safety as the most important additional feature. So there's safety. And this and is important because if we're looking for both at the same time, that means both out of everybody, right? So because this is and not given, we want the intersection of safety and no out of our total. So we aren't limiting our denominator here. We're looking at all 1,092 people because of this word and. We want both things to be true. So 192 over 1,092 is about 1,758. And the closest one to that is A. Cool. If you got C, which a lot of people did, I think what you did was use this as your denominator. Seems to be a pretty common wrong answer. Okay, cool. 6. Scientists estimate that the distribution of the lifespan of the Galapagos Islands giant tortoise is approximately normal with a mean of 100 years and a standard deviation of 15 years. Based on the estimate, which of the following is closest to the age of a Galapagos Islands giant tortoise at the 90th percentile of the distribution? Okay, so when in doubt, draw it out. 50th percentile's right here in the middle. 90th is going to be out here. So we want the age that represents this point where 90% is equal to or below that point. So the mean is 100 years. The standard deviation is 15 years. I'm not going to empirical rule this because 90th percentile doesn't line up with are 68, 95, 99.7. So I'm just going to put the 100 in the middle as a marker. A giant tortoise at the 90th percentile of the distribution is going to be older than that. So I'm going to look at my answer choices. 80 is definitely not older than 100. From there, you can kind of wheedle your way to the right answer, but let's actually calculate this. I'm going to show you two ways to calculate this. First is probably the simplest, it's the most straightforward, because we can do inverse norm. And I know to use inverse norm because I am given a percentile and I want to find a value. So within inverse norm, second bars, inverse norm, the area, always use the area to the left. Some of us have calculators that can actually, we can choose where the tail is, left, center, or right. I always explain it with the tail on the left, because if you do not have an option to choose, it is defaulting to having the tail on the left. So just leave it on the left. So our area is 90%. Our mean is 100 years. Because we know the mean and standard deviation, we can actually pop those straight in, and we don't need to go through a z-score first. So when we do that, got to type that in, 90, 100, 15, tail on the left, we get about 119.22 years. And that is closer to 120 than any of the other answers. So that's our answer. Now, if you were getting a little bit confused or you didn't quite remember about inverse norm, but you are comfortable with normal CDF, we could use our answer choices and normal CDF to eliminate. So let me show you. So let's leave the lower. So if we say normal CDF, and we're going to have the lower as negative infinity. For your upper, we're going to test out our answer choices. So typically, I would actually suggest starting with the number that's in the middle, because if 120 years is too big, we know to go smaller. If it's too small, we know to go bigger. And we've essentially eliminated 3 of 5 answer choices by testing one of them. So 120, let's try it. No, we know that that's the answer. Let's look at 115. What if we just pick that first? So we'll set that as our upper. And then for our mean, we're going to put in our mean and standard deviation. So this is nice because we have the mean and standard deviation. We don't have to go through z-scores. Cool. So this gives us that about 84% of the data is at or below 115. That's pretty close to 90, but we know that we're not at 90 yet, so we should go up. It's close enough to 90 that if I had tested 115 first, I'd probably opt for testing 120 rather than like 130. But at the end of the day, you could test every single one of your answer choices in a problem like this because there's just numbers here. And even if you have to test 4, you will get to the answer. So again, inverse norm when you have the percentile. If you're not remembering, but you know you're looking for it to be 90%, you can use normal CDF and your answer choices and just test them until one of them gives you 90%. Okay, onward and upward. 7. Car rental agency has 2 locations in a city. The box plots below summarize the miles driven for 1 day of single-day car rentals at each location. So this is a box and whiskers plot where any outliers are shown by ending a whisker at the last actual data value within sort of normal, right? So within within the bounds to not be an outlier. And then all of these are beyond that. So it helps you know that instead of this whisker extending all the way to the end here, we know really most of our data is here and we have a few outliers. Same goes over here. Based on the box plot, which statement provides the best comparison of the two locations? So the best comparison. Okay. Comparing has to mean comparing your, A to B. So let's look at A, option A. The number of single day rentals is greater for location A than for location B. In this box plot, we have no idea how many. We know that there are 5 outliers in A and 3 outliers in B. We can see that they have pretty close to the same minimum. We can see that the other pieces of the 5-number summary are more different. But we have no information about the number of single-day car rentals. This is also about the miles, not about the number of rentals. So that's another reason it's out. Same thing, the number of single-day rentals is less for location A than for location B. This is about the miles driven, not the number of rentals, so that's out as well. Compared with location A, the miles driven for location B display more variability and the median is greater. Okay, so let's check that. We're going to start with the median because that is just crispier to identify, right? It is or it's not. So the median on a box plot is this number or this vertical line right in the middle of the box. And for location B, it's definitely at a higher number. It's closer to 100 than the median for location A. So the median is greater. In terms of more variability, even with these outliers out here, the overall range for location A is smaller, and we have a lot more clustering around the middle, right? 50% of the number of miles driven for one day at location A are within this tiny little box, whereas even just looking at the 50% for location B, there's a lot more variety in there. So it also has more variability. This is probably going to be our answer. We're going to check the other ones anyway. It's a really good idea to just look at all the answer choices just in case you didn't actually read what was written there. No shade, we all do it. Compared with location A, the miles driven for location B display less variability and the median is greater. Okay, we do know the median is greater, but the less variability is what makes this one wrong. So then D is out. If it's a little bit wrong, it's completely wrong. Lastly, compared with location A, the miles driven for location B display less variability. Okay, that's already wrong. And the median is about the same. Double wrong. Excellent. Very easy to eliminate this one. So our answer has to be C because it's the only one that doesn't contain a falsehood. Onward. 8. For the purpose of determining the value of its end of the year inventory, a clothing store creates a list at the end of the year of every item currently in stock. Every item currently in stock, along with each item's wholesale price. Which of the following is the best description of the end of year activity? Okay, so if you're cataloging or collecting data from everybody, every item, the entire population, that is a census, like when they do the US Census every 10 years. They're trying to get everyone to respond. So this is not an experiment of any kind because nothing's being manipulated, right? There's no treatments applied. There's no control groups. A sample survey because the store wants to estimate the value of all items. That's true, but it's not a sample survey. Also, D, it's not a sample survey because the items currently in the store are a random sample of all items in the store. Well, they want to know the value of the end of your inventory, not value of items in the store for the entire year. And then E, a census, that's our answer because the wholesale prices of all items. So the key with census is that it's everything. Okay. Good. Was that number 8? Yeah. A grocery store receives deliveries of corn from 2 farms, one in Iowa and the other in Ohio. My boyfriend would find that shocking that they're 2 different places. He loves to confuse the two. Both farms produce ears of corn with mean weight of 126. So I'm just going to start taking notes here because this is a lot of text and I don't want to have to read this 1,000 times. If you can read it a little slower once and get the information you need, you're going to end up in much better place. So the mean for both is 1.26 pounds. The standard deviation of the weights of the ears of corn from the farm in Ohio is 0.1 pound greater than that from the farm in Iowa. Okay, so there is some standard deviation. And I'm just going to say that this is that standard deviation plus 0.01. So we don't know what this S is yet, but we'll get there. Okay. A randomly selected ear of corn from the farm in Iowa weighed 1.39 pounds. So in Iowa, 1.39 pounds, and it has a standardized score. That's a Z-score here for the distribution of weights for weights for the Iowa corn. If an ear of corn from the farm in Ohio weighs 1.39 pounds, how many standard deviations from the mean is the weight with respect to the Ohio distribution? Okay, so I'm going to pause on the actual question because we need to know what the standard deviation is for Iowa, but then we can apply it to both. So standardized test statistic is the value. I'm just going to say actual minus the mean all over the standard deviation, right? And that is on your formula sheet. I think it's the sample statistic versus the parameter or minus the parameter. I'm just going to think about it this way. And that's going to equal our Z-score. So 1.39 pounds. So that's our actual. I'm going to do that here. 1.39 pounds is our actual. The mean in Iowa and in Ohio, but specifically the mean in Iowa is 1.26. And we don't know what the standard deviation is, so I'm going to use an S. We do know the standardized score is 1.645. Now it's just algebra, which I know can be challenging, but we'll survive. So 1.39 minus 1.26, that gives us, let's scooch up here. That gives us 0.13 over S, 1.645. And realistically, the S and that are going to switch, but let's show it happening. So times S on both sides, these are going to cancel out. And then we get 1.645 S, trying to make my 5s and S's look different, equals 0.13. Then we want to get the standard deviation by itself, so we're going to divide by 1.645 on both sides. Oops. 1.645. And we get a standard deviation for Iowa of about 0.079. Okay. So now I'm going to change that. And you don't have an iPad when you're doing this, so I'll treat this like it's a pencil. So I now know that the standard deviation for Iowa is 0.079. And Ohio's standard deviation is 1 pound greater. So 0.01 pounds greater. So I'm going to add 0.01 to that number. And I get 0.089. Okay. So now I can actually answer my question. If an ear of corn from the farm in Ohio weighs 1.39 pounds, how many standard deviations from the mean is the weight with respect to the Ohio distribution. So that's just basically asking, what is the standardized score for that ear of corn? Well, let's find it. Now we're looking for our standardized score. We had an ear of corn weighing 1.39 minus the mean, which is 1.26, all over a standard deviation of 0.089. So when I do this, I'm going to get, again, 0.13 in the numerator, 0.089 in the denominator. And pop that in my calculator, and I get a z-score of about 1.46. That's handy because two of them say that. However, be very, very careful because there are two answer choices that say 1.46. So we can get rid of the other ones. And you might have even wanted to eliminate based on above or below first. But this is a positive 1.46. So 1.39 is greater than the mean, which means we're this many standard deviations above the mean. Make sure when you have options that have above and below, and the rest of it's the same, that you're actually picking the one you mean to pick. Thinking strategically, it might have also been a good idea to just say, oh, this weighs 1.39 pounds, which is greater than 1.26. Looking at my answer choices, let's get rid of everything that says below the mean, because then you can't accidentally get to 1.46 and pick A, which is below. Okay, good. Number 10. The distribution of number of hours worked by volunteers last year at a large hospital is approximately normal, with a mean of 80 and a standard deviation of 7. Volunteers in the top 20% of hours worked will receive a certificate of merit. If a volunteer from last year is selected at random, which of the following is closest to the probability that the volunteer selected will receive a certificate of merit, given that the number of hours the volunteer worked is less than 90? Okay, so this has a few moving pieces. As usual, let's draw a quick picture just to wrap our heads around it. Okay, so it's approximately normally distributed. Great, that's an approximately normal curve. Okay, we know that the mean is 80 and the standard deviation is 7. Again, I'm not always writing in the standard deviations because often we need to get more specific than the empirical rule allows. So volunteers in the top 20% of hours worked will receive a certificate of merit. So I'm going to look the top 20%. This is 50%. This is about the 85th percentile at that inflection point. 84th. So top 20% is going to be something like these guys. I should do it this way. This is my top 20%. So if a volunteer from last year selected at random, which of the following is closest to the probability that they fall in this area, given that the number of hours the volunteer worked is less than 90? So 90 is, I'm just going to pick a random spot and say that this is 90 hours. Okay, so we're basically looking for this area, but we also need to find this area because given always sets our denominator. So let's find that first. Okay. We're at 90. We want to know the percent below 90. So we're going to say normal CDF because we have a value and we're looking for a percent. For the lower bound, I'm going to leave it at -1 times 10 to the 99th again. For the upper bound, I'm going to put it at 90. Mean and standard deviation are going to be 80 and 7 respectively, just from the problem. Mean and standard deviation. Okay. And that gives us, type it in, that gives us a value of 0.9234. I'm going out to more decimal places than I need, just so I can be more certain when I look at my answer choices. Okay. So this right here is the probability of working 90 hours or less than 90 hours. Okay. So now we need to find the probability that we're in this less than 90 hours area, but also in the top 20%. So let's find this value of top 20%. Okay. We're given a percent and we want to find a value. So this is kind of the opposite of what we just did. We're going to use inverse norm. And okay, so our area, if we want the top 20%, but our area is always about what's to the left. If this is 20%, the rest of it is 100 minus 20 or 80%. So we're going to use 0.8 as our area. And again, that's because we want the spot where 20% is above and 80% is below, because that's what adds to 100. So since our calculators give us what's to the left, 80% is what's to the left of that point. Okay. The mean and standard deviation, 80 and 7. And if you have the option, leave your tail left. And we get 85.8913. Okay, so this is the lowest number of hours you can work while still getting a certificate of merit, while still being in the top 20%. Yeah, cool. Now, we have to find a probability of being in this area. So this spot starts at this 85.89. So we need to find the area between 85.89 and 90. Trusty friend, normal CDF. This time, our lower bound is going to be this, because we want the area between 2 points on the normal curve, not just from 1 point and up or from 1 point and below. So I'm going to put this 85.8913 as my lower. I'm going to put 90 as my upper, because we want to know, given that the number of hours worked is less than 90. And then our mean and standard deviation aren't changing, which is small blessing. Okay, so normal CDF, lower is going to be that 85.8913. Upper is going to be 90. Mean, 80. Standard deviation of 7. And we get 0.1234. Oh, that's really fun. Are we done? No, not yet. Almost. So what we have right now, this is the probability of less than 90 hours overall. This is the probability of getting a certificate of merit when you've worked less than 90 hours or volunteered. So we want to know the probability of getting the certificate given that you worked less than 90 hours. So we have one more fraction to set up. And it's going to be, oops, this 0.1234 over the total probability of working less than 90 hours. Divided by, and most of these values are probably in your calculator and you can just scroll up and grab them. You don't have to write out all of it, but you can use all of it. So that's going to give us a total of about 1.1337, which if we round it is going to be our 0.134. So gut checking this, right? Like, does this make sense? 92%, like almost all of this is less than 90 hours. So when we got this being 12-ish%, it makes sense that if we're dividing that by almost 1, we're going to get a number that's a little bigger, but not crazy bigger. I also want to point out this answer is what we got for this portion of what we needed to do. E is what we got for this portion of what we needed to do. But we can't be done with the problem just because we've gotten a number that's in the answer choices. You have to really think about what you're trying to accomplish. So don't be lured in by the siren song of, oh, I got that number, I'm done. All right. Now, full disclosure in a problem like this, when this was actually given as a test, only 21% of the people who did this problem got it right. And that took a while. Like, even though I know where it's going, it still takes some time to just go through the motions. So if you know exactly what to do and you're feeling good with it, go for it. If you're not sure, this would be a great one to throw a guess at and come back if you have time, right? You have 40 questions. You do not have to get all of them right. And it would frankly be astonishing if even one person got all of them right. Like, it's just very, very unlikely. So if this kind of question doesn't feel like something you want to do, don't worry about it. Get to something like this and say, no, thank you. Move on. Make sure to guess, though. Don't leave anything blank. All right. Onward. Resting heart rates in beats per minute were recorded for 2 samples of people. Look at all those prepositional phrases. One sample was from people in the age group of 20 years to 30 years. And the other sample was from people in the age group of 40 years to 50 years. The 5 number summaries are shown in the table. The values of 60, 62, and 84 were common to both samples. The 3 values are identified as outliers with respect to the age group 20 years to 30 years because they are either 1.5 times the IQR greater than the upper quartile or 1.5 times the IQR less than the lower quartile. So, big hint. If you forgot how to find outliers, you need to know how to do that. Your test is probably going to tell you, but probably not right where you need it. So keep that in mind. Using the same method for identifying outliers, which of the 3 values are identified as outliers for the age group 40 years to 50 years? Okay, so IQR is Q3 minus Q1. So IQR for the group in question is going to be Q3, 76, minus Q1, which is 70. So our IQR is 6. So then we need to find our boundaries. So our upper boundary is going to be Q3 plus 1.5 times the IQR. And in our case, Q3 is 76 plus 1.5 times 6. And that gives us 85. Right, 1.5 times 6 is 9, plus 76 is 85. Okay, yeah. So none of these are greater than 85. So right now, I'm going to check. 84 is not above that, and it's above the median, so it's not going to be a low outlier. It's above, like, there's no way. So I'm going to get rid of these. 60, got kind of taken out there with the 84, but it doesn't mean that 60 is out for good. It just means that that answer isn't right. And since 84 can't be an outlier, the 3 values are all identified. No, that's also not going to work. So already I'm down to 3 options instead of 5. Okay. So then I'm going to do the Q1 minus 1.5 times the IQR to find my lower boundary. And Q1 in this case is 70 minus 1.5 times 6. Pop that in your calculator and you get 61. So 60 is not, or excuse me, 62 is not an outlier. It's above 61. It's closer in. But 60 is below 61. So we would consider 60 an outlier. So 62 is not an outlier, but 60 is. So the only option we have left is B. Okay. 12. As part of a demographic study, a college administrator needed to survey a sample of students from the college. From each major offered at the college, the administrator randomly selected 5% of the students with that major to participate in the survey. Which of the following is the best description of the type of sample selected by the administrator? Okay, so randomly selected 5% of the students with that major and from each major. Okay. So looking at our answers, just a quick little review. Because there's any sort of thought, and it's not just they pulled, a random 5% of student IDs and surveyed that people. Looking at C, it's not a simple random sample because it's not simple. It's not a convenient sample. It's rarely a convenient sample, and that's not actually like a valid beta sample. Convenient sample would be if the administrator walked over to the building next to his office and asked the people who were coming out of class there, right? Because it's convenient. We can all hopefully understand why that might lead to some questions about generalizations we can make from that. Next, I want to look at systematic random sample because it's not it. It's the least similar. So a systematic random sample, again, is you like want to survey, X number, X% of a group. So you figure out basically how many you need, and then you survey every like 5th person, right? You pick a random number generator. Okay, we're going to start at the 60th person, and then for 5%, we'd sample every 1 out of every 20 people. So we'd count from the 60th person or wherever we randomly decide to start. And then, okay, we would survey person 80, and then we'd survey person 100, and then we'd survey person 120, just in that list of student IDs. So that's systematic. That's not what's going on here. So what we're left with is cluster sample versus stratified random sample. And this is one that these are two that people often get confused. So a cluster sample is when you're going to survey everyone within randomly selected clusters, right? So in that case, this would be like if the administrator picked, 5% of majors and surveyed everybody in those majors, right? So he surveyed all of the engineering majors, all of the biology majors, all of the dance majors, because those are clusters, but he's asking everyone. So that's not it. What this describes is a stratified, which is where you randomly sample a representative proportion from each strata. And you can think about strata as like a group. So that's what's being described here, because he's getting some people from every major rather than every person from some majors. So again, so this is everyone from some. And this one, stratified random sample, is some from every, some groups, and this is some from every group. So that's what we're talking about here, is some people from every group is represented, are represented. Okay, good. And honestly, like that's vocab. Like learn your vocab. Cool. 13. Graph shows the population distribution of random variable X with a mean of 85 and a standard deviation of 18. Which of the following graphs is a sampling distribution? So this gave a lot of people a lot of pause. Which of the following graphs is a sampling distribution of the sample mean X bar for samples of size 40 taken from the population? Okay, first up, the mean of a sampling distribution will equal the mean of the population distribution. So let's just check for that first. We know that the mean should be 85. This looks like it could have a mean of 85, so let's not take it out. This definitely does not look like it could have a mean of 85, right? 85 isn't even in this graph, so D is out. 85 does look pretty central in B, so we'll leave it. 85 is definitely pretty central in C, so we'll leave that too. 85 is at least in the graph of E, but it is not anywhere close to where the average is going to be. The average is going to be a little bit pulled right by the skew, but definitely not E. Okay. So then what else do we know? For sampling distributions, if the sample size is greater than 30, we can expect a roughly normal distribution, a roughly normal sampling distribution. So looking at what we have left, A, B, and C, A is not roughly normal. So let's take that out too. C and B are both roughly normal, so that's okay. So the big difference then is what to do about the standard deviation. So the standard deviation for the population is 18. The standard deviation for the sampling distribution with a size of 40 is going to be 18 over root 40. And so this is always just the sample size. This is in your formula sheet or on your formula sheet. And so we'll get that this is about 2.85. Just under 3. Now, we know that most of the data should fall within 3 standard deviations of the mean. So let's multiply that number by 3, and we'll get 8.54. So this is 3 times, let me write that there. I'm going to say 3 times 2.85 gives us 8.54. So we should have most of our data contained between 85 plus 8.54 and 85 minus 8.54. That would give us, within 3 standard deviations of the mean. Right away, remembering what this looked like, 85 plus 8 is going to get us over 90. There's nothing over here. This is not going to be it. This one, just to check, 85 plus 8 or 9 is going to put us at 93-ish. That looks reasonable. And 85 minus 8 or 9 is going to put us at, 77. That looks pretty reasonable here. So it's B. Cool. Next, 14. I think I'm going to get to 20 and take a little break, and we'll come back. Biologists studying trees constructed the confidence interval 0.14 to 0.20 to estimate the proportion of trees in a large forest that are dead but still standing. Using the same confidence level, the interval was later revised because the sample proportion had been miscalculated. The sample proportion. The correct sample proportion was 0.27. Which of the following statements about the revised interval based on the correct sample proportion is true? Okay. So the sample proportion is always going to be the dead center of your interval. So the sample proportion here, right, these are 0.3 or 0.6 away from each other. So the sample proportion here was 0.17. So if that's true, then our actual sample proportion, the correct sample proportion, was 10% higher. Let's look at our answer choices. The revised interval is narrower than the original because the correct sample proportion is farther from 0.5 than the miscalculated proportion is. Well, 0.5 doesn't it doesn't seem to play here, but if we think about our confidence interval, right? So we have our p hat plus or minus our z star times the standard error. So the standard error for proportions, and this is where that 0.27 versus the 0.17 becomes important, is calculated as the square root of p hat times 1 minus p hat all over n, all over the sample size. So this takes a little bit of like algebra thinking. Sorry. So if p hat is greater, obviously that's going to shift it up. If we make this numerator bigger, so this critical value isn't changing, our confidence level is staying the same. This sample size isn't changing, it's staying the same. So the only thing that's changing is up here. So let's look at how that number changes when it's 0.17 versus when it's 0.27. So just from the top here, if it's 0.17, then we're going to multiply that by 1 minus 0.17. And we'll end up with 0.17 times 0.83, 0.1411. So that numerator within the radical is this. If it's 0.27, you get 0.27 times 0.73. It's larger. So this number getting bigger is going to make our confidence interval a little bit wider. So the revised interval is narrower? No, it's going to be wider. So we can get rid of anything that starts with is narrower because it's just not going to be true. And we can also get rid of E because it doesn't have the same width. That plus or minus is what determines the endpoints of your interval. So if you're adding and subtracting a larger number, it's going to make your interval wider. Okay. So let's look then at the difference between C and D. The revised interval is wider. They both start that way than the original interval because the correct sample proportion is farther from 0.5 versus is closer to 0.5. That's the only difference in those entire two answer choices. Well, now hopefully it's simple. Is 0.27 farther or closer than 0.17 to 0.5? Well, hopefully you realize that 0.27 is closer to 0.5. So that's why D has to be our answer. This is also why 0.5 is our default. 0.5, having that as the proportion, as the sample proportion, is kind of the most neutral position. So it gives us the widest margin possible, all other things held constant. So that's why we use 0.5 when we don't have the sample proportion. Okay, good. 15. A research organization reported that 41% of adults who were asked, 41%, who were asked to describe their day responded that they were having a good day rather than a typical day or a bad day. So our categories here are good day, typical, or bad. But we're talking 41% of respondents said good. So I'm just going to make a note of that. 41% said good. To investigate whether the percent would be different for high school students, 600 high school students were randomly selected. When asked to describe their day, 245 students reported that they were having a good day rather than a typical day or a bad day. Do the data provide convincing statistical evidence? Ding, 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 convincing statistical evidence. You are going to do a test. Going to be in that test menu somewhere. If you don't do a test and you're like, well, this is because it's a bigger proportion. No, we are definitely beyond that. The proportion of all high school students who would respond that they were having a good day is different from 0.41. Okay, couple of things. Different. That means our alternative hypothesis is that that the proportion is not equal to 0.41. And our null would be that it is. Now, some of you might think, wait a second, how do I know this is going to be one sample versus two sample? This is the 41% that we're testing against. We're not comparing a sample of adults and a sample of high school students. This is just kind of our assumed value. The only sample we have is this 600 high school students where 245 said they were having a good day. Okay, so before we even calculate anything, do we have convincing statistical evidence that it's different? So if the P is low, reject the Ho. So if P is less than alpha, reject. We have evidence. We have convincing evidence. If the P is greater than alpha, we fail to reject. We do not have convincing statistical evidence. So let's just get rid of any answer choices right now that defy the basic tenets of rejecting or failing to reject. So convincing statistical evidence would be yes, because the P is really low. And not having convincing statistical evidence would be that, so no, we don't have evidence because the P is too high. So those are logically consistent conclusions. So here, no, because the p-value is less than any reasonable significance level, that would be a good reason to reject. That would be a good reason to end up with yes. So we're going to get rid of A. B, no, because the p-value is greater than any reasonable significance level. That would be a logical reason to fail to reject. Yes, because the p-value is less than any reasonable significance level. Okay, that's logically consistent. Yes, the p-value is low. Here, yes, because the p-value is greater than any reasonable significance. No. Yes would go with less than in this case. No would go with greater than. And then yes, because the expected value of the number of students who will report having a good day is 246, not 245. That, we are beyond that. We are looking for a p-value. We're not looking for basic proportions anymore. Okay, so now we have to actually calculate this to know whether the p-value is greater than any reasonable level or less than any reasonable level. So to do this, this is going to be a 1 prop Z test and 1 prob Z test, the null proportion, the P naught, is going to be 0.41. That's what this is supplying us. The X, and this is nice because we don't even have to find the number, they gave it to us, is the 245 students who said they were having a good day. N is the 600 students that were surveyed. Just as a side note, because a couple of you have been switching these, X always has to be less than N. We cannot have a proportion greater than 1. So our sample size always has to be the larger number. So 0.41, X is 245, N is 600. And we're looking for the prop to be not equal to P naught, right? It says different, so we're doing a two-tailed test. Here, let's pop that up here. Great, so then we'll go to calculate. And we get, always write down your Z-score and your p-value. So even though it's not an FRQ, do it anyway to get in the habit. Z-score is tiny, so that's a good clue that it's not significant. And our p-value is 0.93. Oh, that's humongous. 38. Okay, so the p-value is, in this case, greater than any reasonable significance level. And you'll notice there's not even a question. That's not even like sneezing distance from 10 or anything, right? That's super far away from any significance level. Okay. Number 16. 80% of the first half. The director of a community recreation center conducted a 6-week study to examine the effects of 4 types of exercise: strength training, flexibility training, aerobics, and jogging, on maximal oxygen consumption. From the 40 members who participated, the director randomly assigned 10 members to each exercise group, each exercise type. Maximal oxygen consumption was measured for each member at the beginning of the study and again at the end of the study. Okay, so we're comparing, right? It's one of our, we're hitting our components of a well-designed survey or a well-designed experiment. The director examined the change in maximal oxygen consumption for each member. It's probably doing matched pairs. Which of the following statements is a correct description of a feature of the study? Okay. So the study has replication because there are 4 types of exercise. No, the study has replication because there's more than 1 member assigned to each exercise type. We have 10 members with each exercise type, not because there are 4 types of exercise. B, the study has replication because it was conducted over a 6-week period. Again, no, that doesn't matter at all. The replication comes from multiple subjects within each treatment. The response variable is the type of exercise with the greatest change in maximal oxygen consumption. No, the response variable is the change in maximal oxygen consumption. The treatments in the study are strength training, flexibility training, aerobics, and jogging. Seems reasonable. Those are what he's studying, those treatments. And he randomly assigned those treatments, which is why they're called treatments. And then the experimental units are the 4 different types of exercise. No, the experimental units are the 40 people. So the only option here is D. All right. 17. Sean and Evan are college roommates who have part-time jobs as servers in restaurants. The distribution of Sean's weekly income, okay, gonna get a lot of information here, is approximately normal with a mean of $225 and a standard deviation of 25. So Sean is gonna be a mean of 225 and a standard deviation of 25. The distribution of Evan's weekly income is approximately normal with a mean of 240 and a standard deviation of 15. Assuming their weekly incomes are independent of each other, which of the following is closest to the probability that Sean will have a greater income than Evan in a randomly selected week. Okay. Way I think about this, whether it's going to be greater or less than, is thinking about what the difference is, right? So if they had the same income that week, the difference between the incomes would be 0. So I'm going to do this as Sean minus Evan. And you could really do it either way, but I'm going to do it as Sean minus Evan. So my expected mean for Sean minus Evan is going to be 225 minus 240, which is, it doesn't need to be about, that is just negative 15. So I'm going to start a new normal distribution combining the aspects of Sean and Evan. Okay, so the mean right here is negative 15. The expectation is that Sean is making $15 less a week than Evan. If Sean is making the same as Evan, that's going to be $0. Well, 0 is to the right of negative 15. I'm going to put $0 here. And if Sean is making more than Evan in a randomly selected week, we are interested in this area, right? Anytime that Sean minus Evan is positive, Sean has made more money that week. So we have our new mean. For our standard deviation of this distribution, though, we do that Pythagorean theorem of statistics. So what I mean by that is we're taking the square root of Sean's standard deviation squared plus Evan's standard deviation squared. And it doesn't matter that I did minus for the mean. Standard deviation is always plus, because remember, we have to account that 2 people is going to have more variability than 1 person, right? They could be moving in opposite directions. They could be moving in the same direction. So we have to account for that. When we do that, we get the standard deviation of about $29 for the combination. And now we can normal CDF this. So, because we're looking for what's to the right, we're looking for this side where Sean is greater than Evan. We're going to say normal CDF. Our lower bound is going to be 0. Our upper bound is going to be positive infinity. Our mean is going to be negative 15. And our standard deviation, we just calculated, is going to be this 29.15. Okay. It's our mean. This is our standard deviation. This is our upper bound. And again, it's a multiple choice question. No one's going to see your work. Always write it out and label it before you type it in your calculator. One thing I did notice was not a lot of writing on your tests. Don't let multiple choice lure you into thinking you can write less. All right, so I'm just typing this in 9.15. And we get about 0.3034. That's the probability. Luckily, that matches one of our answer choices. And there it is. So I wouldn't say that like the actual steps in here are challenging. Coming up with them is what makes this problem a little challenging. So this is about combining random variables. And the real biggie is that standard deviation combination. Okay, couple more. Cool. According to data from the U.S. Elections Project, only 36% of eligible voters voted in the 2014 elections. Always vote. Whatever, it's our right as part of a democracy. You should vote. For random samples of size 40, so of size 40, which of the following best describes the sampling distribution of p hat, the sample proportion of people who voted in the 2014 elections? Okay. So random samples of size 40. 40 is greater than 30. And I know that seems obvious, but that means if n is greater than 30, wait, I'm making the same mistake. So this is a proportion, not a mean. So it's not about being greater than 30. So to decide whether this is going to be normal or not, we have to be expecting that 36% of 40 is greater than 10.36 40. And it is, it's about 14.4. And then 1 minus 36, or 64% of 40, is greater than 10, which it is, so 25.6. So since both are greater than or equal to 10, we can assume normal. Be super careful. I made the same mistake I saw a lot of folks making on their FRQs. Because it's proportion, percent, we're talking about big enough as expecting at least 10 successes and 10 failures. If it were a mean, we could look at the sample size being greater than 30. Okay, so both are greater than 10. We can assume normal. These are out. The mean of the sampling distribution is going to be the same as the mean of the population. So we know our mean is going to stay at 0.36. So E is out. Okay. And then the only difference here is between the 0.076 and the 0.006. So to find that standard deviation, we would need to do our standard error. And this is on your formula sheet. So we're going to take the square root of p hat times 1 minus p hat all over n. So in this particular case, we're going to say 0.36 times 0.64. Got those from here. All over 40. When we do that, we get 0.36 times 0.64 over 40. We get about 0.076. So that leaves us with C. That's our answer. Good. 2 more. 19. To investigate whether the consumption of beetroot juice, is Dwight Schrute in the building, enhances exercise performance, a researcher selected a random sample of 50 students from all the student athletes at a college. All the student athletes at a college. The athletes in the sample were randomly assigned to one of two groups. Randomly assigned, that's important. In one group, 25 athletes were given a daily dose of beetroot juice, and in the other group, the remaining athletes were given a daily dose of placebo. So even groups, control group with placebo, all is looking good. At the end of 6 weeks of exercise training, the researcher compared the performance of the two groups. Based on the design of the investigation, which of the following is the largest population to which the results can be generalized? So the 25 students, athletes assigned to the beetroot juice, no, like we're doing a sample so that we can say something about a larger population. Our sample, sure, we know what happened to those people, but we want to extend it. Same thing for B. It's more than just the 50 student athletes, right? We can say a little more than that. All student athletes at the college, that's pretty good because we took 50 student athletes from this college. And so we can probably extend this to all the student athletes at the college. All students at the college, definitely not, right? Student athletes are a specific group. They're going to have different habits, different training regimens than all students at a college. So we can't say anything about all students at the college. And then all people who exercise, well, students in college are generally younger, and student athletes are like young and in shape, and all people who exercise, like my almost 77-year-old mother works out 2 or 3 times a week with a personal trainer. I don't think she could do anything to hold a candle to a student athlete at a college. And it depends what division the college is. So It's not going to be all people who exercise. So we're just left with all student athletes at the college, right? It's a specific college. You can think like a D1 versus D3, right? Even student athletes at a D1 school versus a D3 school might have different characteristics. So we're just at the college, but we can say something about all of them, all of the student athletes at that college. All right. And last but not least for now, oh, this is so long. 20. College researchers wanted to know under what conditions people are more likely to complete and return a survey. As part of a study, the researchers prepared 3 sets of identical survey and used 3 methods of delivering and returning the surveys. The methods are described as follows. So in class, surveys were given to students in a class. Students were asked to return completed surveys to their instructor. Pretty straightforward. The surveys were given to students participating in a psychology experiment, and students were asked to return completed surveys to a collection box. Lastly, the dining hall. Surveys were given to students in the dining hall, and students were asked to return completed surveys to a collection box outside the dining hall. The graph shows the percent of surveys returned and not returned for each delivery method. And so under what conditions people are more likely to complete and return a survey? That's big issue. Okay, so here's our data. Which statement about delivery method and rate of survey return is supported by the graph? Okay. There's a positive association between delivery method and rate of return. This is not 2 variables. This is not a scatter plot. We're not talking about association. So that knocks out B as well. There's a negative association. Association is for quantitative. Positive and negative associations should be for quantitative variables, right? An X and a Y axis. C, the number of surveys given using the dining hall delivery method was less than the number given using either of the other delivery methods. These are all percent. We have no idea about number. This is about rates. So we could have given 1,000 in the dining hall and 50 in class. And we have no idea. It doesn't say anywhere here that they were all given the same amount, or that they were given different amounts. We only know about the return rates. So it can't be C because we don't know anything about the number of one compared to another. The psychology delivery method displays the most symmetric results. The other delivery methods display skewed results. Skewed and symmetric are for single quantitative variables, right? Like we're looking at means or we're looking at multiple proportions. This is binary. They returned it or they didn't. So it's not going to be this guy. So we've crossed everything else out. It's probably going to be E. Let's read it just to make sure we didn't miss something silly in one of the others. The in-class delivery method had the greatest rate of return. That's true, right? The rate of return is farthest to the right. And the dining hall delivery method had the least rate. Also true. Return the survey has the smallest percentage in the dining hall. So our answer is E. Cool. So that's the first half. I'm going to do the second half probably this week. We'll also go over it in class. I hope that was helpful and see you soon.